Hello. So today I want to discuss about a problem that appeared in CMI entrance exam 2050. It's a number theory problem. It has also an application of, there is an application of Chinese remainder theorem also. It's really a nice example. So you can watch this and this will give you a general idea to how to solve this type of conceptual number theory questions.
This video is sponsored by Chinta.com. Since 2010, Chinta has trained thousands of students from all around the world in mathematical Olympiads, physics Olympiads, computer science and informatics Olympiads, ISI CMI entrances, and research projects for school and college students.
So let's begin. For the first part, I have to show that there are exactly two numbers in 2, 3, up to 9999, for which a square minus a is divisible by 10,000. And I have to find these values of a. And for given a positive integer n, I have to count the number of a in 2, 3 up to n square minus 1 such that a square minus a is divisible by n squared. And I have to express the answer in terms of n. So let's begin. One thing is to observe that let's try to factor out 10,000 into co-prime factors. So I can reduce my case to co-prime factors modulo divisibility. So 10,000, you can easily factor that out. It is 16 into 625 and this is a co-prime factorization. So 16 into 625 divides a square minus a, that is a into a minus 1. If and only if both of them divide, because they are co-prime, so they doesn't cancel out any common factors. Again, 16 divides a and a into a minus 1, but a and a minus 1 are co-prime. Like GCD of a and a minus 1 is 1. So any part of 16 cannot divide a and a minus 1 both, because a and a minus 1 have no common factors. So this holds if and only if either 16 divides, like we must have either 16 divides a or 16 divides a minus 1. There are no other possible cases. And similarly, either 620 divides a or 625 divides a minus 1. So these are all possible cases. Let's try to reduce it to something simpler. Is this possible that 16 divides a and 625 divides a? Or like 16 and 625, they both divide the same number, like they both divide I exactly, or both of them divide a minus 1. Is it possible? Let's see. In either cases, in the first case we have their product, that is 10,000, also divides a, and in this second case we have 10,000 divides a minus 1. So in this case this becomes a problem, because I need to a was less than or equal to 1099 and a was not 01, but this gives me either a equal to 0 or a greater than equal to 10,000. Here this means either a equal to 1 or a is greater than equal to 10,000. Neither of those case is possible, because we are given that a lies between 2 and 9,999. So these two cases, none of them are possible. So we have only two possible cases. Case 1, 16 divides a. So we know that 625 doesn't divide a. So 625 divides a minus 1. And my case 2. And the opposite thing. That 16 divides a minus 1 and 625 divides a. So let's count the number of solutions a such that case 1 and case 2 holds. For case 1, existence, you can prove it by yourself. That in this case I have a equal to multiple of 16. So a equal to some 16 times k, and I have 16k congruent to 1 modulo 625 is 5 to the power 4. Thus it has a solution. It has a unique solution between 1 and this unique solution is just the inverse of 16 modulo 5 to the power 4. And why? Because ax equal to ax congruent to 1 mod n has solution. If I can guarantee that GCD of a comma n is 1, I can say that it has this congruence has a solution, and x is inverse of a model n and it exists. Here GCD of 16 comma 5 to the power 4 is 1, that is obvious, so I can guarantee that such k exists and it is unique. Modulo 5 to the power 4. But I need to find out, and in this process it's a bit, we have to do a lot of calculations to find. So let's try another way. Instead of writing a as 16k, I know that a minus 1 is divisible by 625. So a minus 1 is 625k. So a is, we can also write a is 625 something k plus 1. Now you also know that a is divisible by 16. So 16 divides this thing. This thing is congruent to 0 mod 16. Now what is 625 modulo 16? We know that 16 into 9 is 144. So this is 1. So this is just congruent to k plus 1 mod 16. So you know that k is congruent to 15 mod 16. And that would imply that k equal to 15 must hold. Why? Because if k is not 15, then k equal to k minus 5, k equal to 16 into some r plus 15. Now r should be equal to 0, because if r is greater than or equal to 1, then k becomes very big, and a is 625k plus 1. In that case, you can easily see that it will exceed 10,000 if I take k to be big. So you can easily see that k equal to 15 is the only solution. Like you can see, like putting r equal to 1 or 2, it will exceed the value of a in the range. So k equal to 15 is the only solution. So a equal to 625k plus 1, that is 625 into 15 plus 1. This is your unique solution in the first case. And similarly, second case also has similar unique solution. I leave it to you. We can do this out. It's not a big deal. So you try that out on your own. Now for part B, let's try to relate it with part A. Because here I had a square minus a, in the part B also there is a square minus a. And for divisibility, whatever we are dividing it, a square minus we are factoring into co-prime factors. That was a big idea. That was a key idea, in fact. So we'll do the similar type of thing in the part B also. So you're dividing a square minus a by n square. I divided by this thing. Let's try to factor n square into co-prime factor, just like we divided 10,000 into co-prime factors. Say n square equal to xy and GCD xy is 1. So I have x divides a into a minus 1 and y divides a into a minus 1. And we get the similar case, like in either cases, like for a particular value of xi, I get two solutions. One is congruent to 0 mod x and 1 mod y. Another should be congruent to 0 mod y and 1 mod x. We know that, like, from part A, the calculations are almost similar. From this part, case 1 and case 2, what we get. So what do we get from here? Like, if I write into n square as product of two co-prime factors, let's see ordered. Like, assume with log that x is greater than or equal to y. No, cannot be equal because they are co-primes. Without loss of duality, say x is greater than y, and I'll see that I'll relate it to the unique solution that is congruent to 0 mod x and 1 mod y. For n square equal to x, y, there is also another solution that is 0 mod y and 1 mod x, but I'll write it, I'll associate with the pair x comma y, but that solution which is 0 mod y and 1 mod x, I will relate it to the pair y comma x. So like y comma x and x comma y are ordered pairs, and that interchanging them is not safe, because for n square equal to x, y, I have two solutions. For one solution I associate x comma y pair, and for the other solution I associate y comma x pair. So for n square, for any factorization, I get exactly one unique solution up to the permutation. Like for each permutation I get exactly one solution. N square equal to x, y, I have one solution, one unique solution, that is 0 mod x and 1 mod y. And yx also, like, we're same, but okay, there is also one unique solution. So for each co-prime factorization of n square into two parts, I get exactly one solution. So the answer should be, we can think that answer should be number of ways to factor n square into co-prime parts. Now how can we do that? Say, let's do a prime factorization of it. p1 to the power some alpha 1, p2 to the power alpha 2, say n has k prime factors, and pk to the power alpha k. So n square is just p1 to the power something, say beta 1 up to pk to the power beta k, where beta j is just 2 times alpha j. It's okay. Now I am writing n squared to be product of two co-prime factors. So these two co-prime factors, now each powers of p, like these factors, they come in some, they contribute to some x and y, but none of the powers, like p1 cannot contribute to both x and y, because if p1 is present in both x and y, then the GCD should be at least p, and that would be a contradiction because x and y are co-prime. So if p1 is present in x, then all the powers like p1 to the power b1, everything must be present in x, because if everything is not present in y, then it should be possible that some part in present in x and some other part is present in y, and that would mean that GCD is that p1 divides both x and y, so they are not co-prime. So as they are co-prime, like each prime, their all powers, they contribute to exactly one of x and y. So each p1 to the power b1, p to the power b2, up to pk to the power bk, each of them, either they totally lies in x or they totally lie in y. So I have k factors. Each factor has two choices, either go in x or go in y, and each choice gives me unique factorization up to permutation. So each of the k factor has two choices. So my total number of choices is 2 into 2 up to 2, that is k times, and that is 2 power k. So number of possible factorizations is 2 to the power number of prime factors, distinct prime factors of n. But we need to exclude some cases, because it is possible that n square equal to 1 into n square and n square into 1. In these cases, my choices of x and y should be clear that should not satisfy the given condition, because n square divides a square minus a related steps, and they don't give me any solution. You can easily check that out. So 1 into n square and n square into 1, these two are solutions that are counted in these 2 to the power many solutions. You have to subtract its two solutions. So my answer, that total number of possibilities is 2 to the power k minus 2. And this is the solution. So just if I define tau of n to be number of distinct prime factors of n, then my answer is 2 to the power tau of n minus 2. This is answer is expressed as in terms of n. This is my answer, and we are done. If you are interested in more number theoretic problems like this, you can follow this channel. This channel has a lot of number theory and interesting problems. Thank you.
Chinta programs are designed for students who are passionate about mathematics, and they are personalized with one-on-one training, individual evaluation, and remedial sessions. The reason Chinta students are successful over the last 10 years because they are taught by mathematicians and real Olympiads from leading universities in India, United States, and Europe. Some of our students come back to teach at Chinta from Oxford, Cambridge, Harvard, MIT, UCLA, ISI, CMI, IITs, TIFR, and IISc. For more information, visit chinta.com.